This is Lecture 5A from Chapter 16 of our textbook, Landslides and Other Mass Movements. Here we see mass movement that has moved from the upper right, driven by gravity, to flow across a 6-lane highway and ramps. The number and size of the excavators give you a great perspective of the enormity of the mass movement. This is a common occurrence in the states of Oregon and Washington and in Lincoln County. As Terry Pratchett once said, gravity is a habit that is hard to shake off. In this chapter, we look at the types, causes, and consequences of mass movement and the precautions society can take to protect people and property from its danger. The information discussed will help you decide where to put your new home or when voting on land use propositions for your community. Earth's surface is not terra firma, but rather terra infirma. It is mostly unstable. The definition of mass movement, or mass wasting, commonly called landslides, is the downslope motion of rock, soil, sediment, snow, and ice that is driven by gravity operating on any sloping surface and characterized by a wide range of rates, either fast to slow. The photograph shows a debris flow over a road. The substrate underlying sloping regions of the Earth's surface, whether it consists of rock or regolith, is under the relentless pull of gravity. A regolith is any kind of unconsolidated debris, such as soil, that covers bedrock. The photograph on the left, the town of Yungay, is perched on a hill near the ice-covered mountain Nevado Huascaran. The image on the right shows that the mass movement buried the town beneath a massive debris flow. A scar is visible on the mountain in the distance. In moments, the town was completely covered under several meters of mud and rock, with only the top of the church and a few palm trees remaining. Over 18,000 people are forever entombed beneath the resulting debris. Could the tragedy been averted? Perhaps. Warnings were given, but the slide occurred during the night and people could not get out of the way in time. Since the tragedy, geologists have discovered that Yungay was built on ancient layers of debris from past landslides. Finally, Peru has enacted laws that prevent new construction in the danger zone. Mass movement is an important part of the rock cycle. It is the initial step in sediment transportation, and it is a significant agent of landscape change. What it tells us is that all slopes are unstable and that they continuously change. Sometimes the changes are from natural causes. However, often it is aided and abetted by human activity. The photograph is of a rock and debris flow down a mountain stream. The slopes are bare due to mass wasting. In general, most people refer to any mass movement of rock and regolith down a slope as a landslide. Geologists and engineers find it useful to distinguish among the different kinds of mass movement based on 4 features or factors. The 4 factors are the type of material, rock, regolith, snow, or ice, the rate of movement, fast, intermediate, or slow, the nature of the mass, cloud, slurry, or distinct blocks, and the immediate surroundings, subaerial or submarine. Geologists use the term avalanche as any mass movement that moves like a turbulent cloud. Five diagrams show 5 different types of mass movement: solifluction and creep, slumping, lahars and mud flows, debris flow, and rockfall and slides. One diagram labeled solifluction and creep shows a hillside with overlapping sheets on its surface labeled solifluction and soil creep. A small slump flows onto a road and damages it. Another diagram labeled slumping shows a cliff face with an exposed upslope edge labeled headscarp. Vertical slices of land slide down the cliff and into the water. A third diagram labeled lahar and mudflows shows a volcano with a slurry flowing down the flanks. A fourth diagram labeled debris flow shows a hillside with debris flowing down the hillside that now has deforested land. A fifth diagram labeled rock falls and slides shows boulders going down the mountain. A cloud billows from a rock avalanche. We will discuss each type of mass movement in the following slides: solifluction and creep, slumping, lahars and mud flows, debris flow, rockfall, and slides. Creep is the slow downhill movement of regolith that is due to the seasonal soil expansion and contraction caused by both wetting and drying and by freezing and thawing. Due to this process, the grains are moved perpendicular to slope upon expansion and vertically downward by gravity upon contraction. A diagram shows a clast rising and falling. The starting and ending position of the clast is associated with the summer slope position of the soil. The winter slope position is above the summer slope position. A second diagram shows a thick tilted layer of regolith as the ground surface. The direction of the creep is downslope. Creep is evident from tilting of landscape features like trees, telephone poles, retaining walls, foundation, and tombstones. The upper photograph shows a retaining wall tilting. The bottom left photograph illustrates creep in a cemetery. The bottom right diagram shows a hillside that has its top layer labeled creep zone moving downslope above intact bedrock. A house has cracked walls and a sagging foundation. Tree trunks are curved, and telephone poles and gravestones are tilted. Solifluction, or slow downhill movement of tundra. In solifluction, melted permafrost slowly flows over deeper frozen soil. This process generates hillsides with solifluction lobes. A photograph shows a hillside that has overlapping sheets facing down slope as its surface. Solifluction. The third type of creep are rock glaciers, which are mixtures of rock fragments and ice. As the glaciers slowly move down slope, rocks are added faster than the ice can accumulate. The rocky debris ride on top of and are entombed within the glacier as it flows downhill, as shown in the photograph. The surface of the glacier has many wrinkles in the downslope direction. The next type of mass movement is slumping. That is the sliding of regolith as coherent blocks downslope. Slippage occurs along a spoon-shaped failure surface. Slumps display a variety of sizes and rates of motion. They have distinctive features such as headscarp, or the upslope cliff face, a bulging toe, or the pile of material at the slump base, and discrete faulted slices. The diagram shows a slump cross-section. A curved underground edge labeled failure surface has directional arrows going down slope. The land that slumps down is labeled slump mass. The downslope edge is labeled toe of slump, and the upslope edge is labeled head scarp. The photograph shows the head scarp of a slump. Slumps are common along river cut banks. Blocks that fall into water are often quickly eroded. Slumps can move slowly. We can observe them develop, and this helps reduce potential harm. The left photograph shows an exposed hillside along a river where people are floating on a raft. The right photograph shows a hillside along an expressway. The head scarp of the slump is forming as the hillside moves slowly towards the road. The next type of mass movement are mud flows. debris flows, and lahars. Their flow is enhanced by water. This type of mass movement flow move at a variety of speeds. They can move faster if they are supersaturated with water on slopes with steeper angles. The converse is true, slower due to less water or lower slope angle. They tend to follow river channels down valleys or spread out into a broad lobe at the base of the slope of mountains. This type of movement can also carry huge boulders, houses, and cars. In this slide, we will discuss a case study of the 1960 Vaillant Dam disaster in the Italian Alps, as shown in the photograph. The geology shows that limestone over shale in a deep synclinal gorge. The shale is impermeable, meaning that water cannot pass through or penetrate the shale. The limestone is fractured and water passes through the limestone and lubricates the shale, reducing friction and allowing the limestone slope and soil to fail and move into the lake. On October 9, 1963, 600 million tons of limestone slid into the reservoir. The reservoir broke and the resulting slurry of water, soil, trees, and rocks destroyed downstream villages and killed 2,600 people. 4 diagrams and a photograph show a landslide that flows into a reservoir. One diagram labeled before shows a reservoir with a dam at the base of Mount Tox flank. A smaller diagram above this shows a cross-section of the valley with shale and future failure horizon areas on the right side. Another diagram labeled after shows debris sliding into the reservoir and displacing the water over the dam, causing a flood. A smaller diagram above this shows a cross-section of the valley filled in by a debris pile. At the center is a photograph showing a new forest growing on the debris. In this slide, we will discuss a case study of the 1960 Vaillant Dam disaster in the Italian Alps, as shown in the photograph on the lower right. The geology of the area informs us that limestone lies over shale in a deep synclinal gorge. The shale is impermeable, meaning that water cannot pass through or penetrate the shale, but instead flows on its surface downslope. The limestone is fractured, and water passes through the limestone and lubricates the shale, reducing friction of the limestone and allowing the limestone slope and soil to fail and move into the lake. This occurred on October 9, 1963, when 600 million tons of limestone slid into the reservoir. The reservoir broke and the resulting slurry of water, soil, trees, and rocks destroyed villages and killed 2,600 people. In the lower left, we see 4 diagrams and a photograph that show a landslide flowing into a reservoir. One diagram labeled before shows a reservoir with a dam at the base of Mount Tox flank. A smaller diagram above this shows a cross-section of the valley with shale and future failure horizons areas on the right side. Another diagram labeled after shows debris sliding into the reservoir and displacing the water over the dam, causing a flood. A smaller diagram above this shows a cross-section of the valley filled in by a debris pile. At the center is a photograph showing a new forest growing on the debris. So a mud flow is a slurry of water and fine sediment that are common in areas with abundant rainfall, like in tropical rainforest and temperate rainforest, where the soils are deep. The photograph on the left shows a mudslide in Nova Friburgo, Brazil, that destroyed many buildings at the base of the hill that is now exposed. The photograph on the right shows the La Conchita slump and mudslide along the coast of California. During heavy rains, the slope gave way and heavy mud flowed downslope, burying houses and taking several lives. The slump began when the road was cut in the middle of the slope, steepening the slope. The rains came and loaded the slope with more weight, the mass overcoming the friction holding the slope in place, and the slide ensued. Any slope underlain by poorly consolidated material can give way to a mud flow or a debris flow. The slide in Oso, Washington in March 2014 buried 2.5 square miles of the valley bottom or floodplain on and across the river, burying the small community of Oso. 41 humans were killed. The sad fact is that the slide occurred in an area of known risk, where multiple slides have historically occurred. 2 photographs show a mudslide flowing into a river in the community of Oso on the river bank. Water overflows around the river dam, causing the slump debris to be washed away. The second photograph is labeled with what a geologist sees. The speed at which a mud or debris travels is dependent on the viscosity of the slurry and the steepness of the slope. On a steep slope, very saturated muds may move over at 100 kilometers per hour. If the slurry consists of mud mixed with larger pebbles to boulder-sized fragments, it is known as a debris flow or debris slide. The photograph shows 2 people hiking on top of rock chunks in the debris flow surrounded by trees. The photograph of a recent debris flow in Utah. Note the chaotic mixture of chunks of rock and mud. Often devastating mud flows spill down the river valleys bordering volcanoes. They are known as lahar. A lahar is a special volcanic mud or debris flow consisting of unconsolidated volcanic ash from recent or ongoing eruptions that mixes with water from heavy rains or melted glacial ice. In this photograph, we see a lahar that has rushed down the side of Mount St. Helens in Washington. This is a lahar that occurred in Nevado del Ruiz volcano located in Colombia, in the Colombian Andes. The volcano erupted the night of November 13, 1985, melting some of the mountain's snow cap. The meltwater mixed with ash and raced down the river valleys, inundated the city of Armero and killing 20,000 of the 25,000 residents while they slept. The difference between a debris slide and a rock slide is that a debris slide consists mostly of regolith. A rock slide consists of rock only. Rock slide debris can move at 300 kilometers per hour on a cushion of air. The movement is sudden and deadly. Somehow this debris and rock slide in Douglas County, Oregon landed on an empty road. I had a student who was pulling a horse trailer who was stopped on her journey shortly after the slide. You can probably imagine how long it took to clear this roadside. Rockfall and debris falls are vertical free fall of mass. When blocks impact, they fragment and continue moving, building up a talus at the base of the slope. They commonly occur when a body of rock separates from a cliff face along a joint. The mass of the rock overcomes the strength of the rock where it connects to the outcrop and falls or tumbles down slope. I have been down slope of a rock fall, and the large boulder about the size of a 2-foot square box rolled 5 or 6 feet in front of me. You have to be vigilant when you examine an outcrop or walk to the edge of an escarpment. There are 3 types of submarine mass movements. Mass movements that occur underwater, that are based on the degree of disintegration of the material in the movement. Firstly, submarine slumps, which are semi-coherent blocks that break and slip down slope. Secondly, submarine debris flows, where the broken material moves as a slurry. And finally, my favorite, turbidity currents, where the sediments are entrained in the water and move as a turbulent cloud or density current down slope. Some turbidity currents are quite large. For example, the Tyee Formation between Newport and Philomath are a series of turbidity currents that dislodged from the front slope of a massive delta that was along the northern slope of the Klamath Mountains. The turbidity flows moved northward over 120 kilometers before they ran out of material. The width of the formation is about 65 kilometers. The thickness is about 700 meters or 2,300 feet. Two bathymetric maps show submarine slumps. Submarine mass movements are much larger than land-based mass movement. They are also tied to catastrophic tsunamis. The left digital bathymetric map shows an underwater slip where its edges are highlighted. The main scarp is on the cliff face. The displaced material moves down from the zone of depletion to the zone of accumulation at the foot of the cliff. The right bathymetric map shows large slumps surrounding the Hawaiian Islands. Two forces initiate mass movement: slope forces and erosional forces. The rock is weakened by fragmentation of the upper crust by jointing and faulting. Once the upper crust is weakened, then chemical and physical weathering produces a regolith. The regolith is much weaker than the solid country rock. The Royce's house near Dotson, Oregon was destroyed by a debris flow that initiated in the hills behind the house. The Royces observed the initial debris flow moving down the creek valley and managed to escape. They were able to save their two horses, Dog and Raven. They returned 3 days later, and this is what they saw. Mrs. Royce said, "There was from 4 to 15 feet of mud, boulders, and trees completely covering our property. The house was a disaster. The whole west side of the house was torn open. The fireplace and everything in the living room was gone. My piano and furniture were out in the fields. There were belongings and pictures floating in the mud clear out to the freeway. The front porch was gone. Our home was no more." Slope stability is a dynamic balance between the downslope gravitational pull, the downslope force, and how the material properties resist motion, the resisting force. Movement occurs when downslope forces are greater than resisting forces. In the photograph, we see several rock avalanches that were deposited on the slopes of the shale. The shale erodes under the sandstone, giving no support to the base of the sandstone formation. The pull of gravity and the weight of the rock overcomes the strength of the resisting force of the sandstone. The cliff face broke loose and toppled onto the shale slope. The downslope forces consist of the weight of the earth materials, the weight of added water, and the weight of any structures added onto the earth materials. The resisting forces equates to the material's strength. It consists of cohesion of the material, that is, the chemical bonds in the minerals, the electrical bonds between particles, and the surface tension between the potentially sliding upper materials and the layer of the material underneath it. And secondly, friction, or resistance to sliding on the surface. The pull of gravity towards the center of the earth has two components associated with it: a normal force perpendicular to the slide surface, and the downslope force parallel to the slide surface. The steeper the slope, the greater the downward force of gravity, and the less the object's resistance to the force. In the image, we see a brick on a sheet of plywood. If we increase the slope great enough, the brick will slide. If we sand the surface of the board and reduce friction more, the brick will slide at a lower angle than example A. In example C, water is added to the surface of the board, and the brick slides downslope when the board is tilted to a lower angle than B. So this tells us that slope angle, smoothness of the surface, and water all enhance the tendency of the brick or landmass to slide down a slope. Friction and cohesion are resisting forces to gravity. Friction is an opposing force when two surfaces are in contact that increases with the roughness of the contacting surfaces. Friction also varies with slope angle, as it is a function of mass and gravity. Cohesion is an attractive force between particles at the atomic level. Loose sand or gravel have little cohesion, but clay particles with charged surfaces have high cohesion. All loose granular material or sediments assume a slope angle when piled, called the angle of repose. The angle of repose is the natural slope due to material particle size, shape, and surface of roughness. A diagram shows two piles on a surface. The pile of well-rounded sand has a 30-degree angle between the horizontal and the slope of the sand pile. The pile of irregularly shaped gravel has a 45-degree angle between the horizontal and the slope of the gravel. The photograph shows the angle of repose for scoria on the side of a cinder cone volcano. Small amounts of water increase cohesion, but add too much and it causes particles to lose contact with one another, reducing both friction and cohesion. Angle of repose, this is the maximum angle of a stable slope as determined by the friction, cohesion, and particle shape. The dry sand in this example has an angle of repose of 34 degrees. Adding a small amount of water partially fills the space between sand grains and actually increases the strength due to cohesion because of friction, ionic, and van der Waals bonding. If you add too much water, it separates the grain too far and it loses its cohesion and begins to flow. The types of failure surfaces include saturated sand or clay layers, joints parallel to the land surface, like a granite dome exfoliating or an anticline or syncline, weak sedimentary bedding such as shale or evaporites, and metamorphic foliation. The diagram on the left shows an exfoliation joint surface parallel to the slope surface, and a block of the surface moves down slope. The middle diagram shows a shale bed on top of others bedding. A block of land on top of the shale moves towards a river. The right diagram shows a foliation plane in metamorphic rock. A block on top of the foliation plane slides towards the river. Sometimes a destabilizing event will trigger slope failure. They can be either natural or anthropogenic, such as an earthquake or blasting. Slope failure may occur when slopes become supersaturated after a long, prolonged rainfall, or if the slope is oversteepened. It may occur to any factor that would change slope strength, such as chemical erosion. Sometimes slopes fail for no discernible reason or triggering event like an earthquake. These are two photos that show machinery used to clean up debris from a slope failure. Ground vibrations decrease material friction. If the vibrations affect an unstable slope, the downslope force takes over. Sometimes vibrations or repeated shock can cause liquefaction and destabilize slopes. Vibrations and shocks are common, such as blasting heavy machinery or trains, and of course earthquakes. The photograph on the left shows large boulders that were dislodged from an outcrop. You can see the drill holes placed in the boulder in the foreground. This small village slid down into a fjord following a seismic event. Vibrations can cause saturated sediments to liquefy. Pore, P-O-R-E, water may slurry clay flakes when shaken. For example, the diagram shows rectangles touching each other and generally oriented in the same direction. After shaking, the diagram shows an arrow pointing from left to right with rectangles shaking. The rectangles are oriented in different directions and mud flow occurs. Saturated sand may be fluidized by shaking or cause liquefaction by the separation of the particles and movement of denser particles downward and water upward. A diagram of the 1925 Gros Ventre slide in Jackson Hole, Wyoming, shows rain falling on a hillside labeled Tin Sleep Formation with a layer of Amsden shale. A river flows through the valley and undercuts the dipping beds on Sheep Mountain. The shale is a potential slip surface because it is parallel to the slope. Rain weakens the Amsden and makes the hill slope heavier. Downslope force causes the rock above the Amsden to start moving. Slide debris fills the valley and a scar is left on the hill slope. Around 40 million metric meters slid 600 meters, creating Slide Lake. Two diagrams show steepening slopes due to changes in slope characteristics by loading or adding weight to the top of a slope and steepening a slope beyond its angle of repose. The left diagram shows a river cutting through land. The land surface in the past had a gentle and stable slopes. The land surface today has steep and unstable slopes. The right diagram shows a hill slope where the land surface in the past had gentle and stable slopes. The surface of the field is now steep and unstable. Removing support by undercutting a slope leads to failure. This may be by natural causes such as a river undercutting and eroding the slope, which steepens the slope and causes failure. It may be human-induced, such as cutting a road or a building pad into a hillside will steepen the slope above and may lead to mass movement. One diagram shows waves eroding the bottom of a sea cliff, causing an overhang and a gap wedging open at the top of the overhang. Another diagram shows the overhang breaking off and causing a rock fall into the water, a common cause for erosion along our rocky beaches. Changes in slope strength due to weathering creates a weaker regolith that can destabilize under certain conditions. Vegetation stabilizes slopes, but the removal of vegetation due to fire or clear cutting may destabilize the slope. The removal of roots destroys the root's ability to hold or bind the soil in place. Also, removal of roots destroys the mechanism for the slow, steady consumption of excess water in the slope. Therefore, the added water adds weight to the slope and encourages slope failure. Water reduces slope strength by adding a great deal of weight by supersaturating the pore space. Water in pores push the grains apart, decreasing the strength of the rock and enabling erosion or disintegration. Finally, water lubricates the failure surface or weakness plane in the rock. It might be a bedding plane, a fracture, or a fault. The diagram shows land near a reservoir with high water table. When the water table is lowered, the potential failure plane dries and becomes stronger. Three general factors dictate where mass movement occurs: relief, climate, and tectonic processes. Relief is the difference in elevation between adjacent high and low regions on the land surface. Areas with steeper slopes have more mass wasting. Climate is the average weather conditions along with the range of conditions of a region over a year. Generally, more rainfall creates more mass movement. The photograph shows bare land where a mudslide occurred on a hillside. The bare land is surrounded by forest and illustrates the combination of two conditions, relief and climate. Tectonic processes influence mass movements. Uplift creates greater relief, increasing the force of gravity and creating steeper slopes. Joints and faults created by uplift aid in weathering rock. Finally, earthquakes trigger motion that leads to mass movement. Rockfall could easily occur in this sandstone that has been uplifted and fractured. Geologic mapping can identify regions at risk by highlighting past failures, such as topographically showing slump headscarps, or by revealing currently unstable slopes consisting of steep slopes or low-strength rocks. Both GPS and surveyed land indicate changes that may have occurred over a period of time. Computer modeling is used to determine or identify areas of potential risk. The computer models use multiple factors to assess the areas of high risk and high probability of mass movements. Some of the factors considered are slope steepness, or the degree of slope, strength of substrate or country rock, the solid rock nearest the surface, degree of water saturation, orientation, that is strike and dip of bedding joints and foliation, vegetation cover, rainfall potential, undercutting potential of streams or roads, and earthquake probability. A flowchart that addresses different aspects of the landscape. This is the sort of tool that hazard managers use to assess the potential of landslides. This is GIS data for a region used to make a hazard susceptibility map of San Mateo County, California, and the resulting combination of the three layers. The GIS map of the three layers show the following. Areas most susceptible to mass movements are areas of past movements shown in red. Slopes underlain by siltstone and mudstone in orange are more likely to fail than areas composed of sandstone and conglomerates shown in yellow. And finally, steeper slopes are more susceptible to sliding than gentler slopes. The map shows that susceptibility is higher on the north side of Butano Ridge, shown mostly in yellow, than the south side, which has more green area. To summarize, hazard maps indicate areas susceptible to future mass movements. The hazard maps combine data from other maps that depict relevant geologic and topographic information. GIS is computer software that is capable of collecting, storing, retrieving, and manipulating a large variety of data sets. GIS can be used to construct hazard maps by comparing and analyzing the assembled geologic and topographic data. How can we prevent mass movements? One way is to revegetate as quickly as possible slopes that are bare. Roots of trees grow through and stabilize the plain by removing excess water due to evapotranspiration of the trees. Also, roots help to bind and re-anchor the regolith. Terracing is another way to stabilize a slope. The diagram shows a hill slope with a house at its base. Terrace steps are carved into the hillside and remove load and catch debris. Two more ways of preventing mass movement are: 1, regrading or reshaping slopes below the angle of repose. That reduces the risk of slope failure. And 2, as seen earlier, this slide shows that dewatering a reservoir with a high unconfined water table stabilizes that once supersaturated slopes. By lowering the lake, you lower the potentiometric surface of the water table, and the potential failure plane dries and becomes stronger. Slowing or eliminating undercutting increases stability. Slope failure is imminent in the photograph on the left. The upper diagram on the right shows a filled channel adjacent to a cliff it was undercutting. A diverted new channel further away from the cliff is carved into the land. The lower diagram shows a pile of riprap at the base of a cliff absorbing wave energy that slows undercutting by crashing waves. Sometimes engineered structures can be built to improve slope stability or to reduce movement hazards that we will see illustrated on the next 3 slides. In the photograph on the left, shotcrete or cement was sprayed onto an unstable surface to reduce rockfall onto the road. Part of the slope was stabilized and the other half was not. We can see rock debris at the toe of the outcrop on the natural outcrop side. The diagram on the right shows a retaining wall trapping falling rock from a hillside. The retaining wall protects the road. The large photograph shows shallow rock staples or rods drilled into rocks to hold loose facing or spalding rock. The inset diagram in the lower left shows rock bolts passing through joints on a hill slope where a road is at the base. Sometimes the rock bolts don't work very well, as shown in the inset photo on the upper right. On this last slide, the diagram on the left shows an avalanche shed diverting snow from an avalanche above a roadway. A car on the roadway is protected. The photograph shows machinery working to clean up an outcrop by using controlled blasting to surgically remove dangerous rock.